Hello everyone and welcome to this lecture on the free vibrations of bars. In this lecture I will explain to you how to determine the response of the bar when it is subjected to initial conditions. So for this we are going to need the equation of motion in its homogeneous form, the boundary condition of the specific problem that we are going to look at, and the initial conditions. And for this lecture, I will still keep these initial conditions to be any general functions for the initial displacement and the initial velocity. So I will derive relations that will work for all initial conditions. So the way of solving this is by means of modal analysis. And modal analysis relies on the modal expansion of the displacement field. And the idea of this is that we write the displacement field, which is a function of x and t, as the infinite sum, so say I is 1 to infinity, of the mode shapes ui that only depend on x times the corresponding modal coordinate eta. So eta is a modal coordinate. And the modal coordinate describes how the corresponding mode shape contributes to the solution, participates in the solution over time. So let's substitute this modal expansion into the equation of motion. In this way we obtain an infinite sum, I is 1 to infinity, of rho a times ui times eta I double dot minus an infinite sum of 1 to infinity ea times ui double prime times eta I itself. And this should be equal to 0. Now, in order to get rid of this sum and find an expression for the modal equations, I will multiply the entire equation by uj and integrate. So we get this sum rho a, and then we integrate over the entire length of the bar uj ui dx. Eta I double dot can be taken outside of the integral since it doesn't depend on x. I is 1 to infinity ea integral times uj times ui double prime dx times eta I itself, and this is equal to 0. At this point, I would like to recall the orthogonality conditions of the previous lecture. These conditions specified that for I is not equal to j, the integrals that we see here are equal to 0, and that there's only a non-zero contribution for whenever I is equal to j, and in that case this first integral will be equal to 1, and the second integral, including the minus sign, will be equal to omega I squared. And this can be seen, the second term should in fact be manipulated by using integration by parts, such that the result is like this. So if we integrate this by parts, we get it like uj prime ui prime. And in this process, I have used the boundary conditions, and I think this is the form of the integral that was really in the orthogonality conditions. So the only non-zero contribution is when I is j, and in this way we end up with the modal equations that are a set of infinite equations. However, they are just simple ODEs and not PDEs anymore. So that is nice. So it's like this, the standard form of an Estorff problem, like so. So I think this is a form of an equation we have seen many times before. We know its solution. We can write it down immediately. We derived it based on Estorff techniques to be eta I at 0 times the cosine of omega I times t plus eta I dot at 0 divided by omega I times the sine of omega it. Alright, so this is the solution in terms of the generalized modal coordinates eta. Of course, again for I is 1, 2 and so on. So the question is, how do we determine the initial conditions for the modal coordinates if we are given the initial coordinates in terms of u itself? So what I'm going to do is I will substitute the modal expansion into the initial conditions, all right? And then evoke the orthogonality conditions again to rewrite them. Let's do that. So let's start by the initial position. So u as a function of x times 0, that this is equal to u0x. Let's substitute the modal expansion, that this can be written as the infinite sum of u I function of x times eta I at 0. Now if I multiply the entire equation by rho a uj and integrate, we obtain that the infinite sum I is 1 to infinity of rho a and then this integral of uj times ui dx eta I at 0 equals rho a times the integral of uj times u0 dx. So by evoking the orthogonality conditions, we see that there is only a non-zero contribution for I is j, and that as a consequence, the left-hand side reduces to 1, and the right-hand side becomes rho a integral from 0 to L ui, since I equals j, times u0 dx. So if you know the mode shapes, ui, if they are mass normalized, and if you are given the initial displacement of the bar, then this is how to compute the initial displacement for the modal coordinates. Now, very, very similar, we can derive the expression for the initial velocity, which is u0 dot as a function of x, by applying the modal expansion on this. So write it as an infinite sum of ui, which is a function of x, times eta I dot at 0. In the same way, we are able to get that eta I dot at 0 equals rho a times the integral of ui times u dot 0 as a function of x dx. So this is the expression for the initial velocities. So again, the strategy is that we use the modal expansion to make coordinate transformation to the modal coordinates eta. The idea is that the differential equations for eta are simple. They are of the Esdorff form, such that we can immediately write down the solution. The only thing we need to do, and that is actually the biggest challenge, is to solve for the initial conditions for which we have found these expressions. So in order to determine the initial conditions, the majority of the work will actually be in carrying out this integral. So I think you recognize that this procedure is very similar to the procedure we derived for the vibrations of strings. I will keep it in this general formulation and not go into detail with an example. I think this gives you sufficient information on free vibrations for now. So the only thing that remains is the analysis of the forced vibration, which I will do in the next lecture. Thank you so much.